All right, we're going to take a look at how you can see an FRQ from the AP exam based on Taylor series. Now, this is just one example. This is from the 2008 exam, question 3. And they give us a table here. So the first thing I want you to notice is they give us this table. And for some function h, they give us the original, the first derivative, the second derivative, the third, the fourth. All these different values. All right, so let's see what the question is asking. It says, let h be a function having derivatives, okay? Selected values of h and the derivatives are in the table, and the function h and the derivatives are all increasing on this interval. Okay, so we knew that. That's just what's in the table. Part A says that we're going to write the first degree Taylor polynomial for h about x equals 2. Now that means our center, c, is going to be equal to 2. So let's write that polynomial. First thing I'm going to do writing a Taylor polynomial is write the formula for it. So this is something you need to have memorized. The formula for a Taylor polynomial is going to be f of c plus f prime of c times x minus c plus f prime prime of c x minus c squared over 2 factorial and so on. However, look, I noticed that they actually only want me to write the first degree polynomial. So I only need to go up to this much, just to that first degree term. So that's kind of nice. And c is going to be equal to 2. So I'm going to plug that in. So we're going to have f of 2 plus f prime of 2 times x minus 2. And okay, technically this should be h. So I'm going to go ahead and make this h because that's the function that they give us in the table. Okay, now, in order to fill out this formula, now that I've written my formula, I need to know what these values are. But luckily for us, they give us those. We don't even have to calculate anything. So h of 2, I'm going to come up and look in the table. H of 2 is going to be 80 plus, okay, h prime of 2, based on my table, is going to be 128. And then we just have x minus 2. So here we go. That is our first degree Taylor polynomial. So that's the first part of that question. And based on the scoring guide, you get 2 points just for writing that. So that's kind of nice. All right, the second part of the question says use it to approximate h of 1.9. When it says approximate, that means that we're just going to plug in 1.9 for x. So here's a way you can write it. You could say h of 1.9 is approximately, if you want to get really fancy, you could call this p, or p of x. And so we could say, okay, it's about p of 1.9, p for polynomial, which is 80 plus 128 times 1.9 minus 2. And if I actually calculate what that is, 80 plus 128 times 1.9 minus 2, we're going to get 67.2. So that is our approximated value. All right, and you get 1 point just for doing that. So we're already up to 3 points here out of 9. And then the final part of this part A here says, is this approximation greater than or less than the actual value, h of 1.9, and explain. So this part's a little weird, but you have to think about what would the graph of h actually look like. And this is where this information in the instructions comes in, where it says the function is increasing and its derivatives are increasing. So that means it's a function that's increasing, and if the slope is increasing, the derivative's increasing, then it's getting steeper. So h looks something like this. It's concave up and increasing. You also could know it's concave up because the second derivatives here are all positive. So that's kind of what h looks like. And it wants to know, is our approximation more or less than that? So here's the trick to this. Look at your approximation. It's a linear function. It's a line. This would be the equation of a line. And if I were going to draw a line touching this graph, right? Because it has to touch at the center, which for us is 2. If I draw a line touching that graph, it's going to be under the graph. It's going to be under the graph. So this is an under approximation. So approximation, our 67.2 that we found, is less than h of 1.9. And we can say something like, since h is concave up and increasing. And this little picture kind of helps to justify it as well. All right, but that part was only worth 1 point. So if you didn't get that, you still could have done really well on this FRQ. Okay, part B is actually very similar to part A. Look, it says write the third degree Taylor polynomial about x equals 2. Okay, that's c equals 2 again. And use it to approximate h of 1.9. So again, anytime I'm writing a polynomial, I like to write out my whole Taylor formula, because that way I can just plug stuff in. So here I go, writing the Taylor formula. And what does it say? The third degree. So I'm going to go up to the third degree term. That's the one with x cubed in it and all the 3's. Okay. Now I'm just going to use the table to figure out what these numbers are. So f of 2, because it's centered at 2, is 80, plus f prime of 2, we already found that was 128, x minus 2, plus f prime prime of 2, or h prime prime of 2, rather, is 488 over 3, x minus 2 squared over 2 factorial, plus h prime prime prime, third derivative of 2, or at 2, 448 over 3, x minus 2 cubed over 3 factorial. And so that is our third degree polynomial. So that's the first part of that question. And yes, it could be simplified further, but no, you don't have to do it to get full credit. But you get 2 points just for writing that. And then the third point on this section, super easy. It wants you to approximate h of 1.9. We're just going to plug in 1.9 for x. So 80 plus 128, 1.9 minus 2. I'm literally just plugging in 1.9 to this polynomial that I have. And I'll save you the time. I put that in my calculator and I got 67.988. So there is our approximation. All right, now the third part gets a little trickier because it's talking about the error bound, the Lagrange error bound. It says use that to show that the third degree Taylor polynomial for h approximates h of 1.9 with error less than 3 times 10 to the negative 4th. Now, this seems like a lot, but here's the good news. We've already done some of it. We've already written the third degree Taylor polynomial. That's what we did in part B here. And anytime it says Lagrange error bound, what I would do is write down the formula for that. So the formula for that is that the error in the approximation is going to be less than or equal to the absolute value of m times x minus c to the n plus 1 over n plus 1 factorial. Okay, now what we need to figure out, we already know what c is. C is 2, okay? And then to find out what like n plus 1 is, remember that's the term that comes next. So it's talking about the third degree polynomial. So our next one, n plus 1, is going to be 4. So this will be the absolute value of m, x minus 2 to the 4th over 4 factorial. And now we just need to figure out what m is. So m is going to be the maximum value of the n plus 1th derivative. And for us, since we're looking at the third degree polynomial, n plus 1, that's the fourth derivative. So we need to figure out what the maximum value of the fourth derivative is. Here's the good news. We have the fourth derivative written in our table up here. So I'm just going to pick the maximum value out of this table. The maximum value of this table, but it needs to be in the interval that we care about. So the interval, the interval that we care about goes from, let's see, we're approximating 1.9 up to 2 because we're centered at 2. So even though this 3 one is here, we don't need to go up to 3 because we only need to be in the interval between 1.9 and 2. So I'm going to go ahead and use this value for my maximum derivative on that interval. So back to my error formula, I'm going to have the error is less than or equal to 584 over 9 times x minus 2 to the fourth over 4 factorial from my error formula. Now back to the question, it says, show that this approximates h of 1.9 with error less than that number. So it's giving me x. X is going to be 1.9. So I'm going to plug that in, 584 over 9. So this is 1.9 minus 2 to the fourth over 4 factorial. And if I put that in my calculator, this number ends up being 2.7037 times 10 to the negative fourth. And guess what? That is less than 3 times 10 to the negative fourth. So therefore, we have shown, all this work we did showed that our polynomial had error that was less than 3 times 10 to the negative fourth. So I know that one's a little bit much, but if you get one about Lagrange error bound, I would recommend writing down the Lagrange formula. You will get some sort of credit for doing that and filling in the pieces, filling in c, filling in x, filling in n plus 1, finding m. Usually if you just use this formula, that will help lead you to the answer. All right. Thank you for watching. Good luck with your studying.